But
Recording is on.
Most importantly, that you are able to work or to fit dynamic models and omnibus models, because as I will show in a follow-up presentation, they are quite useful and more flexible. So the way you will follow up Vasco's presentation is like this. So you'll have some data, then you are going to assess models. You are going to assess your candidate models to look at the diagnostics, goodness of fit, and predictive capacity in order to compare the models and choose the model which is not so bad, because we know that not all models are perfect, to validate and decide. So this workshop or webinar is going to use this sequence repeatedly. So now I am going to start describing the package. So with the package, you will be able to fit primary growth models. And as you know, a primary model describes the growth of a microorganism. And the assumption is that this growth is happening under constant conditions, so that the environmental factors are constant in time. For that, you will use a wrapper called the fit growth, and the response has to be scaled in natural logarithm. And as outputs, you will have the initial population, the maximum population, the maximum growth rate, and the lag time. The lag time if you opt for a full model. For the inactivation models, inactivation models will describe the decline in a microbial population, but you can represent both inactivation or survival during stressful conditions, processing, including heat treatment, or even storage, cold storage. So the wrapper that will be used is fit inactivation, but the wrapper does not transform automatically the response variable, and commonly you will use log 10 counts. The output will be the inactivation kinetics parameter, parameters related to the curve shape, and if you want, you can obtain the time to target reductions. So, for example, if you would like to know the lethality time defined as the time required for X log reduction to be achieved. For example, lethality 7 will be the time needed to achieve a 7 log reduction. So this kind of estimates can also be obtained. And then we move on to the secondary models. So the secondary models are a group of models that will describe the relationship between the kinetic parameters and the intrinsic or extrinsic factor. So the cardinal models is a big family of secondary models for growth. And as you can see in the picture, in this graph, you'll have there, not for the line, but for the full cardinal model, you'll have the representation of the shape of a cardinal model for temperature, where the growth rate is related to temperature. Always, this growth rate must be in a square root when we use the fit cardinal wrapper. This has to do with issues of heteroscedasticity, and so it has to be processed like that, as a square root. Okay, and the output would be the cardinal parameters. So the cardinal parameters are the minimum, optimum, and maximum growth conditions. If we are talking about temperature, will be the minimum temperature for growth, the optimum temperature for growth, or the maximum temperature for growth. In case we are talking about pH, the same, the minimum pH for growth, the optimum pH for growth, and the maximum pH for growth. Okay, but could be also extended to water activity, or even to the concentration of an antimicrobial. Then you will be able to fit dynamic models using this package, assuming that you have a changing condition. For For example, it could be temperature, it could be water activity, could be a matrix that is dehydrating in time, or a matrix that is acidifying in time, or a sample that is stored to ramp temperature. And for this, you have different wrappers. You have the feed dynamic growth, the feed dynamic inactivation, and you have also in prediction mode, predict dynamic growth and predict dynamic inactivation. So it is very common. If you find, maybe you have seen this in different publications, that the validation of predictive microbiology models are often carried out with changing temperatures, storage temperatures, where the experiments consist of submitting or subjecting the sample, the food sample, to ramp temperature in a water bath or in a control chamber. So this is used for validation of a model, and not only because it can also be used not only for prediction, but also for fitting. So, but in this case, you need to have the change in temperature. So the temperature profile, this is the values of temperature in time. So you need another input, no? The time varying environmental profile, in this case, the temperature ramp, but also the observations of the microbial concentration. And as output, you will have the structured parameters, the kinetic parameters, and also predictions if you want to. And the omnibus modeling, and here the omnibus models, okay, this is actually a way of fitting how you want to fit your curves. So the curves can be fitted individually, temperature by temperature or condition by condition, or you can opt for fitting your model as a whole. So you have also this possibility. And for this, you'll use the wrappers fit omnibus growth or fit omnibus inactivation. The structure of the omnibus is a primary model plus secondary model specified together, but we have also to give some information to the model about the random effects. This is very useful. These kind of models are very useful when you have different experimental conditions and you want to preserve a lot of information. For example, you want to determine what is the batch-to-batch variability. You have to fit these models. If you want to determine what is the strain variability of certain pathogen, then you will have to fit this model. Okay, so now I'm going to continue with the next part because I would like to explain. I don't want to dig into the classical predictive microbiology because you will know, I'm sure you know what is primary and secondary. But the objective of this follow-up presentation is that you understand omnibus modeling and dynamic modeling, because I believe that you can really take good advantage of the R package for this kind of models. So in the classical modeling approach, you know that you can have different conditions, different environmental conditions or data obtained, for example, a different pH or growth data obtained a different temperature. And then how was the classical approach? It was to fit a primary modeling, like you see in the graph, a primary modeling as a first step, but for each, like for 18 degrees, you will fit this line, for 21 degrees and so on. Okay, so this was the approach. And it's still, very widely used. And of course, you can keep using it. But under certain circumstances, it is better to opt for an omnibus modeling. So in this primary representation, of course, you have to choose a primary model equation. In this case, what we have here is the Huang model for growth. And when we fit individually a model like this, in this case, we are extracting the lag phase duration represented by lambda, the maximum growth rate represented by mu, and so on. So we will have, if J is the number of conditions, J represents the number of conditions, we'll have J number of lag phase estimates and J number of mu max estimates, the primary models fitted one by one. And the second step would be the secondary modeling. The secondary modeling, okay, now you take this lag phase, this growth rate, and you try to find a relationship of how the lag phase duration changes with temperature and how the growth rate changes with temperature. And you get something like this. You want to represent this in an equation. Okay, so here I'm using a transformation of the lag time duration, which is quite often used, the reciprocal, and they are a quadratic equation. And here I have just a linear model and always with the square root of the growth rate. And I have two secondary models, right? So this is the classical approach. And we have, for every model, you see there is an error, right? This is an error for the primary and error, residuals. The question is, when you determine every point, when you determine the estimates of every point, there was also an error associated to the parameters. And the question is, what happened to the error? What happened to the error about this? Each estimate, you see, the bars are errors. What happened to this error? If I do a two-step modeling approach, I am forgetting this error. I'm not including in my equation this error. So I am assuming that this means that this estimate has no uncertainty. Okay, so like there is no uncertainty or error for both, for the lag phase and the growth. Because this error that you see here does not include, this error, you see in red, does not include this one in the bars. This is a different source. So there is a substantial loss of information in the two-step approach. And then what happens is that when you predict, your prediction band is going to be narrower than it actually is. Okay, so we hang on to this question about the error. When we talk about the error, we mean the standard error associated to this lambda, the standard error associated to lambda 2, 3, 4, 5, 6. Okay, and this error should not be ignored. If we want to predict, we should not lose, we should maintain. So the solution is that we take the whole data. You see, this was if you look at the data points, okay, now do not fit line by line. Take the whole data set and fit all at once. And then you need to use what is called an omnibus model, but statistically it is a nonlinear mixed effects model. At level 1, you will have your equation for the primary model. This is the Huang's equation here. Why did I put this equation? Because I need an equation to represent lag. Sometimes you don't have the lag phase, and then the model is simpler to fit. Because if you do not have the lag phase, also at the level 2, you do not need a secondary model for the lag phase. So meaning that you just have to specify two equations. In this case, for this example, we have the lag phase duration and the growth rate, and I have these are the equations of my covariates. Temperature. I have only one covariate here, temperature. And this approach, where you have level 1, level 2 is called omnibus. You will find this in the literature, like omnibus, like global model, one-step model, or multi-level. All of these, or hierarchical as well. Hierarchical is another name, more technical for this type of modeling. Okay, so therefore, the global model, you have to think that you are going to fit primary and secondary at the same time, but that does not mean that you do not have to see how your growth rate or lag phase duration or death rate vary with with temperature or with pH, because you still need to find the trend. You will need to know the trend in order that you choose a secondary model. There will be no loss of information, therefore the error will be always, the error associated to the parameters are going to be quantified as larger. You will have larger prediction bands also. And it's flexible because you can accommodate different data structure. For example, if you do a full factorial design or a fractional or a nested design, you'll have to specify that in the error structure. What is common in our challenge, when we do challenge testing, what is common is to have a design like this. So every green block is an environmental condition. We have, in this case, temperature 5 degrees and a low pH. Environmental condition 2, a higher temperature, and so on. An environmental condition N. At a higher temperature, a higher pH. In a mixed model, you cannot fit straightforward a regression. Why? Because you have to consider that you have errors that are correlated. Okay, how errors are correlated? Because if you have within a condition, you have replicates. These replicates, you see, the results that you have from replicate 1 to 3 are correlated within this environmental condition. These replicates 1 to 3 are correlated within. Okay, so this is why we need to specify an error structure, because we have correlation. Now, this is a two-level model because we have primary and secondary. And the way to prepare the error structure is like this. I will explain what is the variance between environmental condition and the variance within environmental condition. If you are talking about the variance between conditions, this equates to talk about the secondary model, because you want to know how your covariate, in this case temperature, affects the kinetics, the shape of the curve. Then, so here you put your secondary model, and you add an error, okay, to this equation. But this error, this is a special error because it is called random effects. These random effects, it is always assumed to follow a normal distribution with mean 0 and variance as u. So how can you interpret this? You interpret that this error will be therefore the unexplained part. This is, or the residual between condition variance. Why? Because when you put this equation here, you have a deterministic part. So you have an equation that explains the difference, but there is some error associated. So there is some part that is unexplained. So you can call it residual between condition variance or non-explained variability in a square root of mu max. But there is also variance within the environmental condition. If you are talking the variance within the condition, this is the primary model. And now you have this is your primary model and you have an error. But now this error is not a random effect. This error is the residuals. Okay, so this is proper error. This is a random effect. U is a random effect and E is error. Again, the assumption is that it follows a normal distribution with mean 0 and S squared as the residuals or the within condition variance. So in this way, you have errors, let's call it errors, at two levels. These errors are not correlated. Okay, now suppose that you have an experiment that is more complex than this. This is the normal thing that we do in our labs. But we may want to conduct an experiment testing different strains of a pathogen. So suppose you have different strains of Listeria monocytogenes, and you want to find, your objective is, okay, what is the between strain variability? What is the variability strain to strain? Can we in the future model these strains as if it was only one strain as an average, or there is a significant variability? This is a valid question. So in this case, you see you have your conditions. So the replicates are still correlated. No? The results of rep1, rep2 are correlated within the condition. This still happens. But now all these results belong to LM strain 1 are correlated. You see, the first line, all these results are correlated within LM strain 1 and so on. So this is a nested this is a nested design. And therefore, when we specify the omnibus modeling, we have to give the nested error structure. Okay, because here there are correlations at 2 levels. Okay, or clustering, we can call it clustering. The errors are clustered at 2 levels now. And I will explain. Now we have, in the previous case, we had the variance between conditions. Now you will have the variance between conditions within a strain. Variance between conditions within a strain is represented like this V. And now we have a variance within strains. You see, I have a variance. If I take the whole row of results, now I have a variance within a strain. Mu is now follows a normal distribution with mean 0 and variance as U squared. So if you want to calculate the variance between strains, it will be this value here, and we have to check if this is significant or not. If it is not significant, means that we can drop this term and there is no need to talk about between strain variability. Okay, so this S, if you see S in parentheses J, means nested. Okay, this is understood as nested because the condition is nested within the strain. Okay, this is how you have to interpret. But now you have 2 random effects. You see, this at the same level. This is level 2. Okay, this here is level 1. At level 2, you have 2 random effects. These random effects might be correlated or uncorrelated. This is something we have to test. And then you have the variance within the environmental condition, but now these random effects is called error, okay, or residuals. All the omnibus models are fitted with mixed effects, nonlinear regression. You can use mixed effects linear regression, but if you have sigmoid curves, then you'll have to do it through mixed effects and nonlinear regression. Always you will have to set a type of, you have to give an information on how the random effects are going to be understood. Okay, because it depends on it will depend on how you conduct the experiment or what you want to obtain. If you want to obtain the between strain variability, you need to add it to your random effects. The nice thing about this is that you can predict in the same statement, and you have to know that you will have also a broader prediction bands. Okay, so a mixed effect nonlinear model, it looks like this, can be represented like this. In this case, you have a nonlinear function represented the primary model with 2 parameters. This is a weighable model for decay, so you will have the T and the beta. And then you will have 2 secondary models, one model to describe T and the other model to describe beta. Both are represented by functions, in the first case of temperature, pH, salt, and the second of temperature. Okay, so how do we determine the function? We have to look at the data. We have to preliminary fit the primary models. Okay, so only then we can select the best secondary model according to the shape. And here the important thing is this: what are we going to do with the covariance matrix? Because we have two random effects. These random effects, we can set the covariance SUV, the covariance to be null, to be 0, or we can set it to be determined also, which will be an additional parameter of the model to determine. What are the sources of variability? Between environmental conditions, okay, it can be why we have residual error in the growth rate or residual error in the lag phase. It could be covariates that were not taken into account. So if you have different batches of food that you were inoculated and then the background flora is different, because it depends on the batch, then this will provide error to the between environmental conditions. The within environmental condition is maybe that one day you did your determination in the morning and you put, okay, this is my result in day 2, and I did it in the morning. Then next time you did it in the afternoon, and you recorded at day 3, but you did it in the afternoon. So you misrecorded the time of sampling. It could be an error, for example, you made a mistake preparing your agar or something, then this kind of error will affect the within environmental condition. Now, finally, I want to talk about the dynamic modeling to differentiate from the classical static modeling. But for me to explain this part, I have to go back to the differential form. So this is the primigenous model. It could be for growth or for death. If here I put a negative sign, will be the primary model for death. What is N is the microbial concentration, T is the time, and mu is the growth rate. So here, this is the basic equation. I do not have lag phase. I am only representing the exponential phase. This is the growth rate. Okay. This I can add to this very basic equation. I can add an inhibition function to represent the stationary phase. So what you see in red is a stationary function, but I can also, if I have a lag phase, I have to add also a term, okay? But this term will be called the transition term. So if we multiply the transition term by mu, the growth rate, multiplied by the stationary term, then I will have the general concept of this growth. So if you compare Barangi model with Juan's model, they are derived from the same understanding. Okay, this is the primigenous model. Barangi model has a different transition function from Juan's model. But now let's stick to this one, to this very simple model, okay? Assuming that there is no lag phase or stationary phase. We can integrate this model, no? Because if we pass N to the denominator, okay, we can integrate, right? We can put the integral and move with dt, okay? But wait, maybe we cannot, because this growth rate can leave the integral only if it is constant, no? It's mathematics. This mu can leave the integral only if it's constant. What happened if the temperature changed? What happened if I was having sausages fermenting or cheese maturing? In this case, this mu cannot be treated as constant because this mu is changing in time. So it cannot go like this. This is an easy solution because then I have an integrated equation and it's just a matter of fitting the models all in integrated equation because the growth rate is constant. And this falls in the field of classical modeling, classical predictive microbiology. But In this case, then I have data from dynamic experiments because mu changes in time, varies in time, so I have to fit the model using it as such as differential equation. Okay, in this case, here, okay, the equation, for example, of the omnibus modeling. The omnibus modeling, this part that I show you, the previous part, this omnibus modeling will fall within the classical modeling because they were obtained from static experiments. In the case of dynamic modeling, then I have to solve a primary model that is in differential form with a secondary model. So I have to fit them together, but I have to solve a differential equation. And the example I just said was the fermented sausages. If pH is dropping, pH changing in time, dropping during fermentation, I cannot fit this model, this one of classical modeling. But you will see that many authors do it. But it's not, this is a quick solution, but it's not mathematically correct because we have to fit it dynamically. Here we have I put here two different articles produced by our research group where you can have a look. A dynamic growth model, in this case, was for lactic acid bacteria inoculated in fermenting milk. Okay, so we had pH dropping. And then a second case for the dynamic inactivation was a sausage being matured with addition of essential oil. It was an extract. So as you see, an equation can be as simple as this, no? Just two equations that are coupled. In this case, there was 1, 2, 3, 4 equations, okay, coupled, just to represent this, no? This is something we had to do because we found this was a decay that has a little bit of shoulder and that also had a tail, so we have to represent here shoulder, this term, this is shoulder, the tail, and then this is one equation altogether, the two differential models. This is like this was done to obtain a D value, and this is a Bigelow model, okay, for pH. Okay, so, but you have these papers, you can consult them. And how do we solve these models? We have to use ordinary differential equations, and these equations can be solved. There are different methods. We recommend the fourth order Runge-Kutta method. And the numerical optimization will be done through the minimization of the residual sum of squares. Okay, or we can alternatively use our R package. So this is all the introduction from my side, and I think the questions we can take at the end.
Yeah, I think so. So Vasco, do you want to continue now?
Yes. Thank you. Okay, thank you, Natalia and Jen, for the invitation. Thank you, Javier, by making the rules to the workshop. And I would like to thank also to Dimitrios for the presentation. Okay, so Ursula uses for the first time the name Omnibus. So I believe she is the right person to explain the concept of omnibus model, and I will now go by showing you the package and give you some examples how you can use it. Okay. So the package was accepted by the CRAN project, so you can find it in the CRAN website, but you can find it also in the GitHub. So if you want to contribute, your contribution will be welcome. You just can make to report issues or to give some contribution to the models. This is open, so you can study and can contribute if you want. you have also a website for with a better explanation of all the functions. So you can come here.
We cannot see your screen. We're not seeing your screen.
No, so I forgot to share. Okay. Where? Okay. Okay, so I was explaining the packages on the CRAN website, so you can install it directly from CRAN. You can install it also from GitHub repository. So I was telling you that if you want to contribute, or if you find some bug, or if you want to add some functionality to a different function, this is open, so you are welcome to contribute. And we have also this website where you can find all the reference to the functions. Okay, so we have a section of fitting wrappers, so you can find the fit grow, the fit activation, fit cardinal, and in this function we'll show you all the models that we have available. I will show you. Then we have a section of omnibus modeling, so you can find it. We have a section for model comparison, so you can make diagnostic of your models and compare different models, different solutions. We have a section for full grow models. Okay, so in this moment we have 4 implemented: no lab grow models, reduced grow models, inactivation grow models, and also cardinal grow models. And you can find also some data sets that you can use to test and to experiment the functions, and they are examples. So before you use your own data, you can look at this data, see how they are organized, and you can then pass to the using your data. You have also a dynamic section for dynamic modeling, and you have also one assistant. We are in the era of AI, so we developed a small AI agent to help you using the package. Okay, so now I have one presentation I have also one script that I can share with you at the end, but I believe for now I will follow the script that Ursula already talked about this, so I will skip it. The wrappers, Ursula did this, and okay, so we will think when we are working and when we are modeling, we need to think on reproducibility. Okay, so we can use a model. It's not a curve. Just a model is not just a curve. So we need to explicit data processing, how we document the response scale, how we need to give reproducible starting values. We need to apply diagnostics and some comparison criteria for models and for different fitting strategies. And of course, at the end, we need to have some biological interpretation. Of course, the validation is also important because we fit a model, and if you want a model to predict, then we need to validate the model. It's a very different thing to fit and to predict. Okay, so to start, you will need this package, the PredmicroR. After you install it, you can install it from GitHub using DevTools or using remotes, but you can do it also directly in R, just typing install.package PredmicroR, and the package will be installed. If you are in Windows, maybe you use the RStudio, so you can go to RStudio and install the package directly in the RStudio. Okay, so it's important to know that our functions they are in time of response. We have for grow models we use natural logarithm scale. For the activation we use the log10 because the models are more or less prepared to do this. And for the cardinal models, I believe you already know, we need to model the square root of the growth rate. For the dynamic models, will depend. We can use one or the other depending on the data and on the function that you want to apply. Okay, so if you use this function, PredmicroR models, you can take a vision of all models that we have in the package, considering the grow, the inactivation, and cardinal. You have the model name, the response scale, and the parameters that we need to define or to fit as starting values for each model. If you are interested only on the grow model, so then you can put this argument on the function grow or an activation or cardinal, then you will get only the models for this specific task. Okay, so I will make a small example of the primary grow. So you already know we want to estimate the grow parameters from time data that we collect in different conditions, maybe at different temperature, at different food characteristics, or whatever. So we have different environmental effects. In this case, is temperature. So if you are talking about a full grow model, we need to have a national population, a maximum population, a specific maximum specific grow rate, and also the lag time. If sometimes we don't have a lag time, so we can use a different model without a primary model without the lag phase. You can find it in the PredmicroR. In this case, I will show you how to fit a model. To grow rate, in this case, it's a data from Clostridium perfusion, and the first thing that we need to do is to read the data, to import the data to the environment. In this case, we have this function, read the lim, but you can use other functions like read CSV. I like to read CSV also, so but in this case, this is another example, but they do the same. So you need to read the data, in this case in CSV format, but you have also a package and functions to read Excel files, so you can import also Excel files. So I'm reading the data and I'm storing in this object. I call it grow_CP for Clostridium perfusions. Okay, so this function add will show you the first 6 lines of the data. And if you want to understand the structure of your data, then you have this str function. The meaning is structure, and you can see that this is a data frame, and this data frame has 37 observations. That means lines and 3 variables, columns. Okay, so the columns are time, temperature, and the natural log scale of the n. And you can see the type of variables, numeric, integer, and numeric. So it's always good to start to understand what we have in the data and what kind of columns do you have, because sometimes you need to transform the columns or the data in order to fit the statistical models. Okay. So if you want to check your experimental design, your data distribution, I wrote this function to just summarize the data. So in this case, I group the data by temperature, then I summarize, I get n, the minimum, maximum, and the max value. So if you run this code, you will get this table. Here you can see we have 3 temperatures, and for each temperature you can see the number of observations, the time, the minimum time, the maximum time, and also the minimum and maximum for the response variable. So it's always good, or it's essential, to understand the data, to know well the data for modeling. We cannot model the data that we don't understand, that we don't know. Okay, the next step is to plot. In this case, we have 3 temperatures, the different environmental conditions. So we need to plot for the 3 temperatures, and I use this ggplot function to fit it. So I will not explain this code because I'm sure that you already use it in your work, but you can see that we have 3 nice grow curves. Okay, now we check that we can fit a full grow model. So I will choose the one model and I will fit it. First, I need to fit different. I need to fit the model for each temperature. So for now, I need to split the data in according to the temperature. So I do this. I use this function split. I use the data set, and I will split it by temperature. So I will get the data for each temperature. Then I can fit it. I will use this lapply function. This lapply function allows me to apply a specific function to a vector or to a vector or to a list. So you can use this and join this lapply to the fit grow. This fit grow belongs to the PredmicroR, but this lapply is a general function from R. Okay, so in fact I'm just trying to do this in one step to get all the three curves fitted in one step. Okay, but this belongs to the PredmicroR, so you need to say the data set, you need to define the model, you need to define the time, usually is time, and the response. In this case, a grow model should be on the logarithmic scale. Okay, and for this, very, very important, you need to find the nice starting values. Sometimes if the curves are very different, this can be a tricky work to find the correct or the good initial parameters for the optimization. So we run this code now, and I extract the grow parameters from the fit, and you can see we have the parameters for each curve here in this small data frame. Okay, so I get the names and I put the parameters by temperature on a data frame. So this is the data frame that you can see. Okay, so just so this is the first example how you can fit a grow model, and you see that the temperature can affect the grow curves. It's obvious. So you can read the primary grow model. Let's say we for different temperatures we need to find the parameters for the initial value, for the maximum value. So we need to get these values. The Numax, you already know this, measures the steepest growth rate, and the lag time estimates the adaptation period. You all know this, so this is not a big question. In the PredmicroR, we have also one function that the name is PredmicroAugment. It's a function to augment your data set and augmented the data set with the fitted values, the residuals, the model that we are using, and the type of model. Okay, so this can be useful if you mix different models and you get different results. Then you can plot and you can summarize the data according to model or according to the type of the data. And these fitted values and the residuals are also nice to validate the fitting. So this is from the PredmicroR, but all these are general R functions. This is from the base R, and this is from the PredmicroR function, okay, package. Okay, so now it will be good to check if the fitted values have a nice adherence to the observed values, and you can do this. You see, we go to get the grow augmented data that we augment with the residuals and the fitted values, and then with the ggplot you can add the fitted values, okay, as a line. So the lines are the fitted and the dots are the observed values. So we can see that the fitting is quite nice just looking at the graphs. So we need also to check the quality of the fitting. You can look to the graph. We have a nice vision, of course, but it will be always good to check the distribution of the residuals in consideration to the fitted values. We want a nice distribution around this zero line, and we can see that for all the three conditions that the distribution is nice. Okay, so grow now in activation. In the inactivation models, we want to modify this the microbial survival, as Ursula explained to you, or we want to the reduction during the processing or stress or storage. So the objective is to measure the survival or the reduction. Is the same, but with different scales. So when we want to do this, it will be good to have some fitted survival curve and the biological meaning for the parameters. Of course, we want to have a clear view of the replicates variability, because we need to work always with the variation. That variation is important because we model variation, but if the variation is too much, then can be not controllable, and this will be a problem. Of course, we need to have also some metrics for to check the fitting quality, and it will be also good to check if you can extrapolate if the model can extrapolate for different conditions that we don't test it. Okay, so I'm using a data frame that is in the PredmicroR. The data is from one experiment that we did in our lab using the Vixina as antimicrobial. So if you want to pull the data set, just write data Vixina and you will have access to data. And in this case, I'm making a summary of the data. So I'm saving this inactivation summary from the Vixina. I'm doing a pipe. I am grouping by time, and then I summarize. So then you check the head of Vixina, and you can see that we have time, repetitions, and the n in natural logarithm scale. If you ask to see the inact summary, you can see that we have time 0, we have n 3 repetitions, then we have the mean and the standard deviation. So this is the result of this code. So we are summarizing our data. Okay, now we want to see how the microbes evolve along time, and the best way is to plot it. So you can come here, and this ggplot code will give you this nice curve. So you can see that we have a decline a long time. So we have space to model inactivation. Okay, so for fitting this, it's a simple curve, so it's easier. We don't need to split for different environmental levels. So we can use the fit inactivation curve directly, the data Vixina. You choose one inactivation model. I choose the Wellwool Mafarat, so you can. There are other models that you can test according to your data, the time, the response, and also the starting values. And in this code, I'm just putting all the parameters from this fitting in a data frame, and you can see that we have the parameter name and the estimate. Okay, you can extract other information, but this is just to show you how you can use. Okay, so if you want to translate this into biology, into biologic terms, you can say that the Y0 estimates initial microbial contamination. The sigma is the characteristic time scale of inactivation. And if you have the alpha, if alpha is 1, gives you a log linear decline. If alpha is higher than 1, indicates a shoulder-like curvature and an increase in decline. And of course, if alpha is lower than 1, indicates a tailing, so the shape will be different in the decrease in decline rate. Okay, so it will always be good to have knowledge about the parameters and the meaning in order to interpret the results. Okay, so if you want to fit the observed versus the observed plot, if you want to check the plot or plot the data observed versus the fitted values, we have the same. You can use the predict augment function. You get the augmented wave file. Then you can make a distinction for time because we have different repetitions, and then we go to the ggplot and you will get this nice curve. So you can see you have the observed values and you have also the limits, the standard deviation along each dot, and the line is the fitted values. Okay, so if you want to check the quality of your fit, you have a function, fit metrics. So this fit metrics will compute this all these metrics: root square mean, error, mean average error, R square, adjusted R square, IC, BIC. So you have a lot of the metrics that you can use to compare models or to compare sorry, to compare, let's say, different repetitions or whatever. So you can check this fit metrics and you will find a nice set of metrics. Okay, so we want to check also the fitting quality. So we need to plot the residuals against the fitted values. So you can see you have also these these are regular functions from the R software, but in this case I'm using the ggplot to do this graph residuals versus fitted values. Normal, you can do it with a simple plot command, but you can do it, make it more visual appeal, with a better visual appeal using ggplot. Okay, so if you want to diagnostic and compare models, you need to go to these residual plots, root skew error, root mean square error, IC, BIC, parameter uncertainty, biological plausibility. So you need to do all these steps. So if you want to compare different curves, and in this case I'm using the example from the GROW model. You can use the lapply function to apply the fit metrics R function to the GROW fits. Okay, and then you will have the fitting or the fitting quality or the metrics that evaluate the fitting quality for the three environmental conditions. So you can test. Of course, if you have just one, like in Weibull model, we just would fit metrics and you have the stats here. Okay, so if you want to compare models, then we can use also the function compare models. This function belongs to the PredmicroR. So I need to fit a different model because previously I used the one model, but now I will fit the Barani model only to the 35 degrees GROW curve. For that, I use the function fit GROW. I subset the data by getting the temperature 35. I define the model, I define time, the response, the starting, and then you will get the results on this object on the Barani 35. And then you just need to compare models and define your one model and your Barani, and then you will get side by side the metrics for each model. So this is a useful function. If you have different models, then you can take a look to the metrics to compare. The models can be independent. Let's say the data can be independent, but you can have, let's say, nested models. So you need to choose the right statistic in order to compare models according to your situation. Okay. Okay, so I will go back. I will pass these two slides, and I will now talk about a little bit of the dynamic modeling. You know, Ursula explained this very well. So we need this kind of models because when we have the environmental conditions changing a long time, everything is different. So we need to be able to take this into account. So in the static model, we have a question: what is the growth rate at 15 degrees? But when we have temperature variation, the question is what population trajectory results from the complete temperature history. So what will happen a long time if the temperature is changing. Okay, so the dynamic workflow, you need to define and inspect the environmental profile. You need to select a dynamic primary model. You need to link these environmental conditions with the secondary model, and then you need to simulate the trajectory to estimate the parameters from the observations. Okay, of course, you need to diagnose the fit and also to test the parameter sensitivity. So in this case, the ODA are important. You need to use it, and they will accumulate the effect of the previous conditions. So we start on the time zero, and then these differential equations help us to accumulate a long time. Okay, so we start necessarily with the profile. So I'm just simulating a dynamic profile. You can have your profile, but this is a simulation just to show you how to use it. So you have this function to define a dynamic profile. You need to have in a dynamic profile, you need to have time and you need to have temperature, of course. So this will define our profile, and if you ask for the profile, you will see that we have time and temperature. So this is our profile a long time with the fluctuation in the temperature. If you plot our profile, we're using the ggplot, using these data exactly, so you can check and you can see the fluctuation. And here as a red dot line, you can see the minimum temperature that allows for growth. It's just an example. You need to find these values for a specific bacteria, no, for specific microorganisms. So, but in this case, we use this. So that means in this area we have growth, but in this area we don't have growth. Okay, so we have the profile. So now we can predict the growth using this predicted dynamic growth. You need to feed the profile. You need to feed the model that you want to use. In this case, we are using the one model and the one square for the primary model and the one square root model for the secondary model. Of course, you need to give the starting values and you need to give the times that you want to predict. Okay, so if you run this code, then you will have the output, and in this case, I'm just applying. I'm selecting a subset of the data by time, temperature, and log n, and I'm showing you the first 8 lines. Okay, so these are the data that we simulate. Okay, so if you want to connect this to the exposure, let's say the curve with the profile with the growth, with the curve of the growth of the microorganism, then you can make these dynamic panels. You use this. This is a function that that change your data set. So I'm getting the growth period, I'm getting the time, and I'm getting the temperature as value, and I'm putting the panel as temperature. So if you execute this code, then we pass this data to the ggplot, then you can plot together the evolution of the microorganism and the evolution of your profile, just to have everything together. So if you want to check with the realistic data, then we can define a grow data. In this case, I'm simulating the data. So I create an index, and then I'm using this function to simulate the data. And of course, these are the data that we simulate. And then if you want to fit the dynamic grow, you can do the same. Let's say you have your function fit dynamic grow. You need to have your data that we simulate. You need to give the profile, the time, the response, the same, the models, the starting values, and of course you need to, if you want to estimate. In this case, I'm using the function to estimate the model parameters. In this case, I'm just estimating the A parameter from the secondary model. Okay, so I have this experimental data that I simulated, and then I want to estimate the parameter using a dynamic experiment. This is also possible. You can estimate the parameters from the primary grow model and also from the secondary grow model. Okay, so this is the one square root secondary model. I just put it here to show you. So we have 0 when the temperature is lower. The temperature is of grow is lower or equal to the mean, and you have this function for the grow when the temperature is higher than the mean. The mean is the limit for the microorganism grow. So if you want to check the fitted versus observed, you can do also the PredmicroR augment. You augment our data set with the fitted, with the residuals, and then you can plot with the ggplot the observed values, the dots, and these are the fitted values, the line. Okay, and we have also the metrics that to evaluate or to analyze or to evaluate the fitting quality of our model. And to finalize this dynamic model, it is important to do what we call the sensitivity analysis or scale sensitivity of the model parameters. This is important. So we have a function that calls that the name is dynamic sensitivity, where you can calculate where you can do this analysis. So what you need to feed, the type of model, grow. You need to feed the profile. You need to feed the model, the primary and the secondary, the starting values, and the times that you want to do the analysis, and then you can plot these results, and you can see the A parameter will have a positive and higher, bigger sensitivity, scale sensitivity, but the T-mean will have a negative, higher, but negative scale sensitivity. And between 0 and 10, both are more or less 0. How do you interpret this? So if the A's parameter presents a positive sensitivity, so means increasing A increase mu max. Okay, whenever the temperature of the environmental temperature is higher than the mean. Okay, so the grow becomes faster, so the predicted population increase. The effect accumulates during the warm part of the profile. For example, for the T-mean, we saw that the a negative sensitivity. Okay, so increasing T-mean narrows the temperature range that permits growth. Of course, if we increase this T-mean, the difference will be close to 0. In the limit, if the T-mean is equal to the T at time T, this difference will be 0. So the growth rate and predicted final population decrease. So that's why sometimes if you want to fit to estimate these parameters, no, you need to do it where you have scale, where the parameters are sensitive to the environment. If you come here, you don't have conditions to estimate the parameters, because the sensitivity is close to 0. So this is important if you want to plan an experiment and you want to estimate the parameters for a specific grow conditions. Then this scale sensitivity is very important, because you can see where you need to work in order to have a nice precision in the estimation of the parameters. Okay, so now the omnibus modeling. Also explained this very well, so I will not spend too much time reading this. But what I choose an example that is very difficult, because it is an example with a lot of data and different conditions, and the shape varies a lot between or among conditions. So sometimes when we have a lot of this variation, can be difficult to find good initial values to have a convergence in the model. Okay, so we have a data set that I named with omnibus.csv. So the first thing I need to do, I import the data set, and I do some mutation to the data. The data set is in log 10, so I change it to logarithm scale. I change the unique experiment condition to a factor, and I scale also the temperature, and I compute these new terms, then the square of temperature and the square of the PredmicroR. So sometimes it's good to pre-process the data in order that we can use these new variables, these new columns in our models. If you take a look now to the structure of the data, we have the condition, we have the index experiment, so we have 96 experiments, we have some repetitions, okay? So we have repetition 1 and 2, we have the temperature, the cinnamaldehyde, and the PredmicroR, time, log 10 scale, initial value, log n0, the microbial in the logarithm scale, and also the initial value in the logarithm scale, the temperature squared, and the PredmicroR squared. So just some modification to check. Okay, so if you check this, I made a small subset, just keeping the data because the data is too big. The data with the cinnamaldehyde and PredmicroR with the 0.5 and 1, but this is an error here, so I need to copy. Okay. Okay, so if you take a look to the data, you will see that I filtered here by the original data. I filtered in order to have less conditions, because I show you that we have 96 conditions, so we have less here. But this is enough that to show that the shape of the curves are very different, no? And the time also with a lot of variation. So this can be tricky to fit because the conditions are very, very different. Even the shape are not exactly the same. So we have a challenge data set to fit. Okay, Ursula already explained this, so I will just put it smaller in order to see. This is the model. Okay, I will test the model with the initial value at population level in the initial concentration, and then we will put the K parameter depending on temperature square, PredmicroR, and cinnamaldehyde, and also the alpha parameter will be affected by the temperature and the temperature squared. Okay, so I grouped by the individual curves. We can do it by condition because in the individual curves, for a condition we have two individual curves. So we need to process the data, and then we can fit it differently. But in this case, I just checking and explaining to you how you can use the package. So I define the group as the individual experiment. Okay, and we also put some random effects on the K and alpha, and just as intercept. And of course, this transformation is to improve the numerical scaling. Okay, so this will help us to have better convergence results when we are fitting the model. So the model is this. Ursula explained this very well, so you already know. I will not spend more time with this. Okay, so now how we will fit this? We start with the data. I'm just getting some information from the data in order to get some initial values that I can use in the model. And I don't have output here, but I can show it. You can see it then in the script. Okay, so now to fit, you have the function fit omnibus in activation. We need to give the data, the augmented data set that we prepare at the beginning. We need to define the primary model. We will I don't remember exactly. It's a Weibull specification that we have in the package. The time, the response, the group. The group is important, so we need to define the group. Then,
sorry, Vasco, this is a Weibull for 3 terms.
Yes, for 3 terms. Yes.
It's not for only K and alpha. It's for Y0, initial concentration, curvature.
It's the model from Peleg and Wang. Okay. This has a meaning. It's Peleg and Wang. So you can find it in the PredmicroR package, the explanation, but you can have also the paper and check it. So the secondary model will put the intercept in the epsilon0, and then we are saying that the K and the alpha are affected by these environmental conditions. Okay, so you need to put a random also. I will put a random effect on the K and alpha. We can define also the correlation structure. In this case, is null, just to show. And then the starting values. Starting values, it's important. You know, we are using the scale natural logarithm, and in our data we have the data in the log 10 scale. So we need to convert this to the natural logarithm scale. Okay, then you can find also the method to test the models. You use maximum likelihood. Then to fit the final model, you can use REM, restricted maximum likelihood. Okay, this is not so nice to see, but I will pull down. Okay, so now you have the output of the fitting. So we have the fitting quality metrics. You have the random effects. Okay, so you have here the random effect for K in the intercept, for alpha on the intercept, and the residual. All these are the variance of the model. Okay, so and in fact we are extracting some variance from the data in order to be able to detect some difference in the effects. Okay, so you have also the fixed effects solutions, the parameter and the standard error and the p-value. Maybe we can think on this. Maybe we don't need it. And then we have also the correlation among all the parameters that we have in the model. Sometimes you can see that we have some, they are very correlated. Okay.
Vasco, can I explain that a little bit more if you go up?
Yes, you can.
Because I want to explain this is very important, the error structure. So you see their error structure, it is, you will find a standard deviation. That standard deviation in my slide was as S, it was a variance, no? It was S, U, and SV. So in this case, the SU is K. For K, there are two parameters, K and alpha. So you have to understand this as a residual. So with that equation, you explain the variability with the covariates. That was the carbachol, cinnamaldehyde, and temperature. But there was something residual. And that residue is represented by the standard deviation. So it's a type of, you can understand as random effects or error. And they are at the level 2, because these belong to the secondary model. But here Vasco opted for a solution that where you have covariance, because you see the correlation, 0.6. It means that those residuals are correlated positive. So the higher the value of the residual, in K is associated with higher values of alpha. Okay, it's correlated. So meaning that we cannot set this correlation to 0, because I told you that you can opt for a simpler correlation matrix, but in that case, it's 0.6. It's high. This is a correlation coefficient between K and alpha. So you have to keep it. And the residual, it is the error of the primary model. Okay, this is the residual, the error E that went plus E of the primary model. But there is something interesting here, is that the residual is lower than the residual for K. No, for the K has a standard deviation that is higher. And for alpha, you could explain with the equation better. Then when you go to the fixed effects, you can see that there is an intercept for K that you can drop. So meaning that you can do K like this. K equals temperature. K equals temperature plus temperature squared by dropping K intercept. So you set intercept to 0. K equals temperature plus temperature squared. But for K you do for alpha you do need the intercept. For alpha you need the intercept. So for alpha you have alpha equal A plus or beta 0 plus beta 1 temperature plus beta 2 temperature squared, because all of them are significant. Important is also to look at the correlation matrix, because you want to avoid having correlations higher than 0.9. When you have very high correlated fixed effects, the models become unstable. You will have the model will be unstable. So meaning that if you slightly change the initial parameters, maybe it will not converge. That's it, Vasco.
Okay, so in fact, with these random effects, we are extracting the variability from the K and alpha in order to see, this allows us to observe better the other effects, okay? So we are extracting the noise. When we use these random effects, we are catching noise that then you can compare or check the difference for other parameters. Okay, so if you want to see the metrics, we have this fit metrics. So you already see this function. So we have the metrics, so you can compare. And of course, we have also a way to extract the fixed effects using the NLM package. Is a different way, but you have it here. And now let's look of the result. We will obtain the fitted values with the PredmicroR augment. So we store it in this augment omni, and then I will display only this data for cinnamaldehyde 0.511 and carbachol 0.511, also to be more restricted, and then we plot it. And you can see the observed values and the fitted values. So you can see some curves are more nice than others, but of course this is also connected to the data and to the shape of the data that we have. Okay, now if you want to take a look to the diagnostics, if you get the residuals from the data and you plot the fitted versus residuals, you see that you have a lot of work to do. Okay, so when I look to these residuals, what can you see? the residues are not symmetric around this 0 line, so there is a lot of work to do in order to find a good model, in order to have these residuals nicely distributed around around the 0. But this is just to explain, so I don't need to find a better model, but you can do it in the future. So this is an example of something that you don't want to have in your final model, okay? In this case, for the temperature, you see, for the temperature 60, 65, 71, they are quite different, no, from one temperature to the other. So that means that we need to look for a better model. Okay, I added also some check of the biological plausibility. So I added some code in order to compare the observed with the estimate, okay, and the fixed effect for K and the fixed effect for alpha. You can see that for the observed values, we have the minimum 17 and the maximum 20. And for the epsilon 0, we have 19. So these two are very close. Okay, so if you take a look at this, they are very close. They are plausible. If you have in the estimated 50 or 60, they are very different from the observed value. So this is the observed, the estimated, they are close, so makes sense. And for the K, you can see that you have the variation from minus 0.0 to 15. This show you the variation that we have in the curves. So our experiment has a lot of variation in the shape. So that's why these fixed effects K are so different. No? So we have curves with this value minimum, and we have a curve with the maximum. For the alpha, the values are more close, so they are not so different. But the K are making a big effect in all this modeling. Okay, for model decision, you need to be before using the model, you need to take some consideration, the intended decision, the data range used for fitting. You need to think on that. You need to check the response scale, what the response scale that you need to use, the selected model and the parameters that you will use, the final model, the best model that you find. Of course, if you want to select a nice model, you need to be based on the evidence of diagnostic, evidence of validation, and of course, you need to define also the limits for extrapolation. Sometimes you can extrapolate, but you need to know exactly where you need to go. Okay, so to finish, as an advice, if you want to keep your analysis reproducible, you need to save the raw data separately from processed data. You saw that I was always changing the name of data because I want to keep always the original data, and then I will process and give different names in order not to lose my original data. Use scripts, not manual steps. Record units, response transformations, put everything in your script, fit the candidate models with transparent starting values, and compare statistically and biologically. You need to compare the models because the parameters can have different meanings, okay? Statistical and biological. So evaluate before you need to use this model to decision making. The resources you already saw, and I will finish just show you the example of the PredmicroR system. I ran it before because this can be a little bit slow. I will show you. So we have if you go to R, you call the PredmicroR, then you can launch this shiny package. This is a shiny web, a shiny package and interface. So you write PredmicroR Assistant app, and you will get this Shiny app open. You can import your data set. And in this case, I'm using a data set for a grow model. Trace just to check. So you import, you define the separator, the column separator, the decimal that you use, depending on the type of data that you have. Then you have the assistant. If you have Oyama in your computer, you can. We have also a deterministic solution, but in this case, I have Oyama, and I'm using Llama 3 Grok tool use 8B. So this is a LLM for tool use, and you can ask. You can have you have some typical questions, but you can write your question. Okay, so you can come here and you can type your question. So I typed fit a primary grow model and explain the response, and I asked to generate the analysis, and the LLM, the agent reads the data set and give you a QR code to fit your data. So if you have data and you test it and you find some errors, or if you want to give some suggestion, test it and then let me know. Okay. Okay. So just to show you, we have also a way to help the LLM. Sometimes if the data is very complex, can be problem. So we can define the task that you want, grow, inactivation, cardinal. We can define the time column, usually is always time, the response column. Then you can, if you have temperature, if you have pH, or if you have water activity and some inhibitor, then you can feed this information to the LLM, and the code will be suggested according to the information that you have in your data. Okay, so that's all for now. Thank you very much for listening.
Okay. Thank you very much, Vasco, and also Ursula, for such interesting presentation. Also for sharing your time and your expertise with us today. So there are several questions. I don't know, Dimitrios, if you want to start with the first one.
Thank you very much for this excellent presentation, both of you. Indeed, it is a lot of interest for our participants that raise a lot of questions. And starting from them, the first one is, what's the importance of choosing the proper error metrics for the model? For instance, residual error versus error in the kinetic parameters. How to decide which to choose from?
Okay.
Ursula, do you want to answer?
It's about the error structure. The error structure, it is important because it is linked to how you plan your experiment. You know, you can have different strains, as I put in my example, or it could be batches, different batches of meat, for example, and that means that it has to be accounted. You know, this factor, different batches of meat or different strains, this has to be accounted for by the model, because if you do not account that for, that you are assuming that there is no effect at all, that there is no effect of a meat, or that there is no effect of strain. So you should account it and rather test if there is error or variance coming from these sources. Is there any variance coming from different batches of different meat that you bought in time, or any variance due or error due to the different strains that you tested? So you have to account for that. Therefore, when you build up the error structure, like I explained with Vasco's example, you can choose a diagonal structure, a diagonal error structure, or a natural error structure. So my advice is to start with the diagonal. You can start with the diagonal because it's the convergence is easier because you have one less parameter to estimate, which is the covariance. With a diagonal structure, it's easy. So meaning that if you have some issues of convergence, you can look at the initial values of the parameters and just focus on changing the initial values. Now, once that you were able to attain convergence, means that you chose the right initial values, then you can escalate and do the natural error structure that will take into account the covariance, because then your model will be more stable to determine an additional parameter. So that is the answer. That's my advice also. Do you want to add something, Vasco?
I would like, but I don't remember the question anymore. So if somebody remember the question, maybe I can add.
It is in the chat, Vasco, if you want to see.
Where is the chat?
Is the
Okay, the chat is here. So where is the
importance of choosing the proper error metrics?
What's the importance of choosing proper error metrics?
Yeah, so I understood the question. Is it important that you model also the error structure? Is it important? Yes.
The residual errors versus error in the kinetic parameters. There are different things, no? So the residual error is one thing. The error in the parameters is another thing. So of course we want parameters with small errors, but not always a small error is a small error, because depending on the magnitude of the parameters, the error can vary a lot. For example, if you are estimating the error of the lag phase, okay, the lag or the initial value, that is a value close to zero. A small error can be a big error compared to the parameter. But if you are looking to the growth rate, when the growth rate is 1 or 2, then the magnitude of the error will be dispersed in the magnitude of the parameter. Usually the parameters with lower magnitude, they have bigger errors. So of course we want to have the less error in the parameters, but that comes from the quality of the data also, always. Okay.
Okay, thank you, Vasco. The second question is about the material. I think that is available, right? It's open source.
It is. If you go, I show you in the beginning. This is our package in the CRAN, but I can show you also. Let me just share. Okay, if you go to this website, you can see all the functions that we have. So you have a manual here. You have some examples how to use it. Okay, and we have also some vignettes where you can read with data. So you can get the data. If you install the package, then you have some examples how to fit. Okay, this is a little bit different from what I explained today, but you have for grow, for comparing predicted models. You have also for dynamic. you have for omnibus, and also for microbial activation and for cardinal. So this is open. You can read it and you can check it. For the functions, you have here in the manual. So all the functions have an explanation and an example how to use it. But you can have also in the CRAN you have sorry, you have a manual. Where is the manual? Here you have a manual, so you can download the manual to have the functions, and of course you have this GitHub where you have all the code and also some explanation. So, but we can share the presentations with you, and maybe you can share the presentations with the audience.
Also, the theoretical presentations I have already sent them.
Okay, good.
Okay. There are another question is about I will read it. In all these modeling approaches, how do we account for the intrinsic uncertainty of the CFU counting method used to gather the raw growth inactivation data? Do we consider it's constant across all environmental condition tested? I will copy and paste also in the chat.
That's a $1 million question. That question is a question. Let's say I start to work with in microbes with Ursula when she came to work in Bragança, and one thing is certain: the variability that we can have in the experiments is very high. So when we prepare an experiment, we need to train the method. We need to assure that we are doing everything with precision. Because if we don't do the experiments with a lot of rigor, then we can have a lot of variation. Of course, we cannot avoid the variation between days or between foods, but we can account we can account that in the model. Let's say we can make an experimental design in order to confound these effects. So if you have, let's say, 2 temperatures or 3 temperatures in 2 or 3 foods, or then you need to make an experimental design in order to test this in different days, in different runs. You need to have runs in the same day for, so this is an experimental design. But the main thing that I think is very, very important when you talk about this kind of data is the inherent variability of this microbiological data. So we need to be very, very precise. We need to train a lot in order to get the good results. And of course, sometimes if you go to see some data, we see data points that are very close. So in fact, there are some previous work that shows that the variability that we can have in these measures is around 0.6 log. So if you are measuring at day 1 log and at day 2 1.2 log, we are measuring error, because the variability that we have in this technique is higher than .2, So we need to define the experiments in order to have a nice difference between the first point and the second point. Because if you shorten the time and you have the data point together, they are not different. So you are measuring noise in the data. So this is very important. You can control with the nice train, you can control with the experimental design, and of course also with the time points that you choose along your experiment.
Thank you, Vasco. Maybe a couple more questions, I guess. Yes. Dimitri, do you want to continue with the next one?
Yeah, we have a challenging one. What are the limitations of omnibus modeling compared to the classical two-step approach? So what are the opportunities and limitations, maybe?
Ursula, do you want to respond?
Yeah, I think as limitation, the only limitation is that you need to know better to program. I think that this is the only, because in terms of prediction and estimate, it is better, because as I explained in my presentation of Omnibus, on the contrary, you are not losing any information. You're not losing information. You are accounting for the experiment that you did, either full factorial, fractional factorial, or nested design in the same code. And even in the same code, you can do the predictions. So there are only gains, but I think the only limitation is that it's more time consuming, because it's like you cannot work blindly. You still have to do some primary fitting, because you need to know the secondary model, how it looks like, the trends. You still have to look how growth rate is evolving against temperature. What is the shape of growth rate against temperature, or what is the shape of lag phase duration, or what is the shape of the D value, for example, against temperature. You need to look at that, so it's more time consuming.
I will add also, Ursula, that because we use mixed effects models, the mixed effects models have nice properties, because they are very, very good for these nested designs, and we can have the best of the two worlds, no, the frequentist statistics and from the Bayesian statistics. So it's more complex. I show you the data in our example, a lot of conditions and a lot of different shapes of the curves. These make the convergence of the model very hard to find. So that's why sometimes it's difficult to use this one-step approach, but I think is much better. And Ursula do that very well. So with the mixed models, and the mixed models are very, very good. So I advise you to learn and apply it, because you are one step ahead when you use this mixed model.
Thank you very much for your responses.
Yes, there is another question. Maybe this could be the last one. It's about what do you think? What do you see as the next major step for PredmicroR? Quantitative microbiological risk assessment, tertiary models.
There is a backend song. I didn't listen very well.
What is your outlook for the package? What you are planning more to add to the package?
Okay. So we can add more models, and we can add more algorithms, new algorithms, let's say maybe the most important area now is the artificial intelligence. Okay, so we have already a small agent there, but I think there is space to grow in this area of the LLMs to use, and in order to automatize the code, and to get the code, and to suggest the code.
Okay, and Dimitrios, do you want to finish with the last one?
Yeah, and another last question. How could these bacterial growth models implemented in the software be applied to fungal growth, given that the stationary phase is often not considered? So, can this model for bacteria be transferred for fungus? Would any modification to the model function be required?
Will you answer, Ursula? I believe there are specific models.
Vasco, you can answer by the models that are supported. What are the primary models supported? Because the models supported also describe the full phase, no? The stationary too. Which models are supported? Which primary models are supported? Can you answer, Vasco? Which primary models are supported?
The primary models, we have several primary models. Complete primary models, we have the Varani, the Wang model, the Rosso model, and the Zwittering model. So I believe for fungus, you need to check if the data is similar or if the models can be applied, because I never worked with the fungus grow, but I believe it is possible. No, some of these models can be used in different kind of data. If you have a grow curve, you can apply it, but then you need to adapt these parameters to the biology of the fungus. No, because the grow of the fungus is not the same as the growth of a bacteria. No, the bacteria grows by dividing 1, 2 to 4 and so on. No, but the fungus is different. But of course, if you have data like that with a sigmoidal curve, you can fit it. But the question is, how do we interpret the parameters? But I will suggest to check if there are some models developed or parameterized to the fungus growth, and then you can check.
Okay, thank you very much, Vasco. So this was the last question. I would like to ask if you want to turn on your webcam, because we are going to make a screenshot without the assistant, without the participant for the social media. And also, while the people turn on the camera, again, thank you, Ursula, thank you, Vasco, for your time, for your expertise. Was a very, very, very interesting workshop. That's all. I'm going to take the screenshot. People here.
Thank you for the invitation. It was very nice to be with you.
Our pleasure.
Yes, thank you.
Okay. So this is the end of the seminar. Thank you very much also to the assistant for coming. That's all.
Thank you.
Javier, did you take the photo?
Yes.
Okay.
Okay, so we can go.
Thank you. Bye-bye. Bye.
Thank you very much.
Thank you very much
for being here today.
Bye.
See you soon.